So part 2 of the module is about dimension reduction methods. So our data matrix, X, we normally think of it as having n rows, where each row represents an individual. And on each individual, we think about having p different bits of information, so p columns in our matrix. Now, if the number of columns in our matrix or our number of covariates is too large or is large, it can be very difficult to visualize the data, to model the data, and to think about the data clearly. So one stage of statistical analysis is to try and reduce the dimension of your data, to go from having p bits of information about each individual to, say, r bits of information, where r is much smaller than p. If you think about kind of common data sets that companies might hold on you, so Amazon or Google, or whatever, they might store millions of pieces of information about you. Now, in order for them to extract value from you, to sell you things or to sell information about you to companies, they need to summarize that data and find, the useful bits of information in there. Okay. So they're going to try and take these million bits of information and reduce it to a small number of pieces of information. So you might buy a book on fly fishing in Northumbria, or you're interested in a holiday to Tenerife, or whatever the information is you want to extract about you. They're going to try and take lots of bits of information and reduce it to a small number of bits of information. So that's what this part of the module is about: ways of reducing the dimension. So there are lots of different methods for reducing dimension, and they differ primarily in the type of data they work with and what their aims are. But they all have some characteristics in common. So typically they are optimization problems, and they're trying to find a reduced dimensional version that retains, in some sense, the important information, where what is important varies from method or problem to problem. So why do you want to reduce dimension? Well, if you have 1,000 bits of information on each p person, but you find that you can reduce that to just 2 or 3 bits of information, it means we can plot it clearly. Or it means we can store it more efficiently. Or it means we can model it more easily. So in this part, there's 3 chapters in this part. There's, first of all, principal component analysis, which is a widely used method in statistics. The aim in principal component analysis is to find the dimensions in the direction data, or a reduced dimensional summary of the data that maximizes the variance in your reduced kind of coordinate system. There's canonical correlation analysis, which imagines you have 2 different data sets, and we're going to try and maximize the correlation between different summaries of them. And the final bit is multidimensional scaling. That's going to be in chapter 6. And in that, the aim is you're just given a distance matrix and you want to find a number of points in low dimensional space that have those distances in between them. Now, it's probably not going to be a surprise to you that all of these methods are going to involve a lot of matrix algebra. In particular, the singular value decomposition and the eigen decomposition are going to appear time and time again. So just a warning then. So the warning is that in high dimension is not like low dimension, and our intuition can lead us astray in high dimensional data points. So to illustrate this, I put a simple example in the notes. So let me share my screen. Okay, so what I want you to think about is, let's simulate 100 points in 2 dimensions, and we're going to pick them uniformly distributed between 0 and 1. Okay, so I've got 100 points in 2 dimensions. Okay. The x variable is between 0 and 1, the y variable is between 0 and 1. 100 points here. And we can think which 2 points are farthest apart here. Okay, so let's find that out. So you can look at the commands in your own time, but let's compute the distance matrix, find the maximum distance between the points. Okay, so it's probably something from the bottom left to the top right corner, or the top left to the bottom right corner. Okay, and just for illustration, let's plot that on. Okay, so these 2 points are the points that are farthest apart. So they are 1.2 units apart here. Let's find the 2 points that are closest together here. Okay, so that's these 2 points here, and they are 0.01 units apart. Okay. So let's take the ratio of these two things, the maximum distance divided by the minimum distance. Max dist divided by min dist. Okay. So there's a ratio there of 111. The maximum distance is 111 times bigger than the minimum distance. Okay, so that's 100 points in 2 dimensions. I could do that many times. Okay, I could repeat this procedure to work out what on average is the ratio of the maximum distance to the minimum distance. Okay. Now what's interesting is that if we do this, okay, we get that ratio changes as the dimension increases. Okay, so I've got a plot here where I've got this ratio of the maximum distance to the minimum distance. Okay, and so here was the point with 2 data points, 2 dimensions. Okay, that's the situation we're considering. And for each dimension, I had 1,000 data points. And I did what I just showed you. I repeated that 10 times. Okay, so I generated 1,000 points 10 times. And each of those 10 times, I found the maximum distance and minimum distance and worked out the ratio. So on average, in 2 dimensions, I got max distance and minimum distance to be this number up here. This is a log scale, so I'm not quite sure what number is. It's probably about 3,000. Okay. Then I changed the dimension. Okay, so instead of having 2 dimensions, I tried 5 dimensions. Okay, what I had to do in 5 dimensions, the ratio of maximum distance over minimum distance decreased. Okay, so then it only had a ratio of about 40. Okay, and so on. As I increased dimensions, the ratio, the maximum distance to the minimum distance, decreased till it was about 1. So when it's 1, that's saying the maximum distance is, on average, the same as the minimum distance. Okay, so think about it for a minute. 1,000 points, when we put them in a 1,000-dimensional space, 1,000 points randomly distributed in 1,000 dimensional points, on average, the maximum distance between any 2 points is about the same as the minimum distance between any 2 points. So in other words, all the points are the same distance apart. So that's kind of really counterintuitive, but it's there to illustrate how big space is, how big high dimensional space is. 1,000-dimensional space is huge, and we can't really comprehend that because we are used to thinking in 2 or 3 dimensions. So the point of this part of the module then is to think about reducing the dimension, going from this high dimensional space and trying to find low dimensional projections of the data that are interesting and informative and useful in some sense. Okay.